Let's start with the basic Uber design. I just designed some of the design already, and then later on there will be some. It is not 100% design. It has some draws, some bottlenecks, some trade-offs which I still need to complete. But some of the basic design I have completed, and then whatever will be the remaining, I will be doing that while recording this video. So yeah, let's start with the basic Uber design. What are our functional requirements? What are our non-functional requirements? And our calculations, bandwidth, estimations of the basic microservices. We will start with each of these, and along the way, I will keep on explaining. I have written down some of the trade-offs. I have written down some of the steps that how we will be handling all of these. So yeah, let's start. Let's start with the basic Uber design. What are our functional requirements, which normally the interviewers ask, and it is the responsibility of interviewing to mostly focus on these. During the interview, it is best for the interview that he doesn't diverge from these functional requirements. And if the interviewer is not asking about the other things, then just keep pinpointing about these functional requirements during the whole time. What is our first one is user will be able to book a ride. System will forward the ride to nearest drivers, and then the drivers will pick up the ride, and we will be having the different driver statuses, ride statuses. So three main entities which are coming to my mind for the ride statuses. I have written these down in the database schema, not here. And then what are our non-functional requirements become? Obviously, our system will be highly available, always, all the time. Doesn't matter 24/7. Riders should be able to book their ride, so it should be highly available, and it should be partially consistent as well. So we are mostly focusing in our system highly available, but it should be consistent as well in case of like when the ride is in a search phase. At that time, one driver at a time should only be assigned to one rider at a time. So there should not be any confusion. It can only be done if we have a proper mechanism for strong consistency in this phase. So the whole system should be overall highly available, but we are prioritizing consistency partially as well as some parts of our system. I have done some calculations, but my overall concept is that calculations in this such case study where we are designing the whole system, and we will be mostly focusing on the main algorithm, the main searching algorithms, the main connectivity which is being done between the rider and the driver. So in such case of case study, the main calculations are not that much important. We don't need to properly estimate the network bandwidth, how many servers will be required. Such kind of calculations are important if we are mostly focusing on uh, some specific backend application which is not visible to the public, or we have some high constraints that this application will be for some startup where we have some cost limitations, such kind of requirements are present, then we need to properly estimate our calculations. I will be doing some further case studies where I will be doing these calculations as well. I have not completed all of those, but I have estimated some of these, like there will be 1 million daily active users, and if each user performs 10 queries per day, so it becomes about 10 million queries per day, and it becomes about 116 QPS. Not that much traffic. So, and let's say for peak, it becomes 1,000 QPS. Let's start with the main. So we have three client microservices, client driver, and then the web portal for the internal admin staff. API gateway will be doing the right limiting and the authentication part with the help of JWTs or the session tokens, and then the global load balancers will also be present there to properly navigate the traffic to our main node, main pod, main instance of our microservice. Some specific node of the auth. We have these main backend microservices like auth, trip, location. They have figured it out. Everyone has its own uh, way of solving the problem. I figured out by this way. It can have some limitations, which you can point it out. But my thinking was that these microservices are enough to solve our problem. If our microservice will be doing the authentication, this script service specifically will be handling the WebSocket connections during the ride which is in progress. And then we will have a location service. It will be connected to our locations database. It will be a separate locations database here, and it will be a key value store mostly. Let me put it that way, key value store. One more thing about Excalibur here, that my circle should have been properly enlarged when my writing was going beyond the circle. So why it is not doing like that? Then let me cut it down. And now if I will put, then I will circle properly enlarged. Okay. our location service will be getting data from our driver mobile app constantly, like after every 5 seconds, and it will keep on updating our driver's locations database. Our pricing service. This pricing service will be handling the business logics about the pricing. What are the fair estimates about if it will be receiving the starting destination, the ending destination, and it will be properly calculating the pricing estimates mostly. So, and then comes our main matching service. This will be the main match service, like the main function of the Java class. So this matching service will be receiving, it will be handling the connections between all of our other microservices. So, and then the notification service will be doing the part of the sending notifications to the drivers, to the clients during the ride, after the ride. So yeah, that's how it will be. The main database, what I'm thinking in case of this is the AWS DynamoDB, which is the perfect case here because DynamoDB supports both the strong consistency and also highly availability, which we both need in our use case. That's the database which we will be using here. Yes, the matching service will be doing the main part of the connection between these different microservices, and it will be doing the main part here. So, and then we'll be using the event stream platform like Apache Kafka. It will be doing the main as a pub sub event stream here. One service will be publishing the event, and the other services will be subscribing the event from this Apache Kafka platform. So, if there will be some asynchronous communication which we need to do specifically, like in case of notification, then we'll be using the Apache Kafka here. Let's start with our database schema. Currently, core entities will be having three. One is rider, ride, and driver. Rider will be having ID, name, and history. For example, if we are using the proper analytics, history is not that much important here, but I will just return it here. Then ride, the main important entity in this scenario. It will be having the ID, rider ID, driver ID, and then the status ID. What is the current status of the ride, and then the category ID, like what is the type of vehicle we are using in this ride. Different type of rider statuses, ride statuses we have requested, and then the searching, and then accepted, starting, and completed. These five are possibilities. They can be other, but these five will fulfill our requirements. And the ride will be in searching phase. Then any driver will accept this. Then driver will reach at the location, and driver will start the ride, and then driver will end the ride. It will be completed. There can be others like driver not found scenario, or let's stay with these five for now. Driver will have ID, name, history, and status. Driver statuses will be free. Driver is in ride, and driver account is cancelled or whatever. Let's start with these along with all I will answer further. And then the right categories are Uber, Uber XL. These are not very important right now. I want to focus with the basic steps here, like these are our public APIs, and then this is the main section I want to focus properly during the steps. This will properly help us in understanding that how these microservices will be communicating with each other. Public APIs, we have public APIs here. We are assuming that we will be using the REST because REST is most understandable and easily to communicate during the system design interviews. First will be the get request, get estimates, like when user has decided the destination location, and destination starting location is by default understandable from the application. Then starting location can be different as well than the user's current location. System will be receiving the get estimates ticket, and it will return the estimated price. So in the body, what we will be passing in the body, get request, we will be passing the starting location, destination location, and the right category which the user has selected. So this is the first one, and then the other one when the create ride. Create ride will be basically when user has accepted any one of the estimates, then it will request for create the ride. Here, this will be a post request because in this case we will be properly creating our resource. So this will be a creating. That's why it will be returning ride ID and status. Or what we can do is ride ID and status. We can just ride here, right here, right. Whatever in the ride will be, it is properly understandable, and that's perfectly makes sense that it will send the created ride. We will be properly passing the rider ID, starting location, destination location, and the category ID in this scenario. And then our third public API will be get drivers nearby. So it will return all of the nearby drivers. Actually, that will not be a public API. That API will be basically used internally by matching service to the location service. So in this case of API, what I'm thinking is that it will not be a public API. It will be the internal API, or better to use RPC, remote procedure call here, because of the fast communication between two microservices. It's best to use this approach, remote procedure call. So these will be our two public APIs, and this will be the internal remote procedure call. But still, I'm using the REST structure here, but that doesn't. Okay, we have another one, get drivers nearby, and then the update, right? That this will be also the internal remote procedure call when we will be updating the status of the ride into the database using this remote procedure call. And then driver, whatever the ride ID will be and the status of the ride will be updated, even if it is accepted, it is completed, or whatever. And driver ID will not be passed; it will be automatically taken from the token. Two public APIs, and then two internal remote procedure calls. So that's how it will be. Let's start with our steps for a ride.
These are different steps which we have written, and it will properly help us to fill our this sequence diagram here. This is the sequence diagram which I have drawn. It creates all of the different microservices which we have, but I have not fulfilled this sequence diagram yet. I will do this later. For now, before just fulfilling the sequence diagram, what I wanted was to just write all of those steps. It will help us to properly engage our microservices together and to have a proper mind map that how requests are going properly. Let's start with the basic one. Rider will open mobile app. He will be able to see ride estimates. When he will enter starting and ending destination, user can obviously change the starting destination, or mobile app will pick up the default one from its user's current location, and then the ending destination user will enter. So in this case, client will call get estimates API from matching. This is the get estimates API, which we wrote. And what will happen is that client, this is our client, via the API gateway and via the load balancer, this get estimates API will be called, and it will be navigated to the matching service. So matching service will receive that get estimates API. What it will do further, matching service will call pricing service to get estimates. We have handed over this whole functionality of estimations, getting the locations, estimates, these business logics. If we need to integrate anything further, like based on the different locations, it can be different for the different countries based on the traffic. So traffic pricing will be integrated to some other third-party tools like Google Maps, Waze, and it will be properly doing the estimates by estimating the peak traffic time, estimating the traffic, estimating the route. So whatever the logics will be, matching service, the main thing is that matching service will be getting help from pricing service for this problem solving further. And then pricing service has internally different logics implemented to calculate estimates, and matching will return estimates to the client. Okay. Matching service will return back to the same way to the global load balancer API gateway and client to the client. Then rider accepts the estimate and selects the ride. System will start searching the rider. Rider will accept. So in this accepting, what will happen? We have another API. This create ride API. Now this API will be again create ride API will be called from the client mobile app to the matching service. And what will matching service do? Matching service will call that create ride API, and how we are now matching service will needs to create one ride to the AWS DynamoDB, and it will be doing, and matching service also needs to send the notifications to all of the relevant drivers via notification service. Notification service will be using FCM or APN in case of Apple push notifications or Firebase Cloud Messaging to send the notifications to the drivers for all of the relevant drivers to ask them if they want to accept this ride or not. So how will this whole thing be happening? It will be happening using Apache Kafka event stream platform because of the proper scaling issues which we can face if we are not using this such kind of event stream platforms. If we are using just direct communications between microservices, these issues can happen. So just to navigate, just to resolve these issues, we properly use Apache Kafka platform here. Okay, we were using writer accepts the write and selects the write system matching service will publish event in a Kafka with ID. With this event, we'll have different subscribers. DynamoDB will create write against. Okay, now here we have a Kafka present here. This is the Kafka events which we have created. Because of this event observe structure in Kafka, what happens that if one event publishes one event to the Kafka, all of the subscribers will be notified and they will do their respective parts against that event. So when matching service will create this event, write create event into the Kafka, then it will trigger DynamoDB to create a write against this event. DynamoDB can do this part, or we can use some trigger function in DynamoDB which will be doing this part. So whenever there will be this event in Kafka, DynamoDB will create a write against this, and the default value of that write will obviously be requested. We wrote some write statuses, so by default, the status of that write will be requested. And then matching service created the event, and then matching service will also be subscribing to this event. What will matching service do? Matching service will do subscribe to this event, and what will matching service do against that event? Matching service will start searching for drivers against this write and also update its status from requested to searching in DB. So this will be the part which matching service will be doing. How matching service will be start searching for drivers? Matching service will obviously update the database and update the status of that write from requested to searching, and it will also start searching for drivers. To start searching for the drivers, matching service needs help from location service. This is our location service. Location service has information to all of the drivers in some specific area. So matching service will call the via remote procedure call. It will call the location service. That is the important part here. It will not call direct. It will use a remote procedure call to call the location service, and location service will return all of the nearest drivers. And then matching service will call the notification service to notify the drivers. It will not notify those drivers all at once. It will be done step by step. Like based on different priorities we will be having, first driver will be notified, 10 seconds will be given to that driver. If that driver doesn't accept the write, then we will send notification to the next driver for 10 seconds, and so on and so forth until we have consumed, until we have found a match, or until all of our drivers have been consumed. So that's how it will be. Matching service will classification service. Matching service will publish multiple events in Kafka against each driver. So Kafka via the notification service, after publishing, matching service will send server-sent events to client with status searching. So yeah, we also need to keep on informing the writer that your search is in progress. You have to wait for a few seconds, few minutes maybe. And then client will update your write status accordingly on UI. On UI, client will be able to see searching status. And same parallelly, we are informing the drivers getting their status. Driver accepts the write, and let's say one driver accepts the write, then what will we do? We will matching service adjust the status of the driver to accept it, and then matching publishes another event in Kafka, and that will be event create trip, and then we will our trip service will start trigger from in the start of the video. We told that this trip service will be handling the during in progress, right? Okay, now the trip is in progress. Basically, our ride is in progress when matching service created this event. Matching service published one event create trip. So where is our Kafka? This is the Kafka, and then trip service was subscribed to that event. So the Lambda function within trip service triggered, and that trip what will trip service do? Trip service subscribes to that event. Trip will call Lambda function to create dedicated WebSocket connection for both writer and driver to trip. So because the project is in progress, we need to properly create one full duplex connection between client to the server and then for a writer to a server, so that they will be notified accordingly of the existing status of the ride, how much time it will take to reach the destination, and some other things as well, like what is our current location. So to fulfill all of those use cases, it is important to properly create one dedicated in fact not one, two dedicated WebSocket connections here. So, and also one public URL if client needs to share the URL, share the status of the ride to some other member, to some family member. So that's what also Trip do. Trip also creates one public URL to be shareable for the other ones as well. So we are not focusing on that public URL right now, but we are mostly focusing, and I have also not covered the technical architecture of that public URL. I've just mentioned it here. So we are mostly focusing on that client WebSocket connection and then the driver mobile app WebSocket connection here. Okay, now the public URL is being created. When the write will end, then what will happen? Driver trip will create an event and trip event. Driver will stop the write. Our trip service will create an event and a trip, and this trip will also end these WebSocket connections. This end trip event, what will happen? End trip event. I have not written that end trip event here. So I can tell directly that what will happen when this end trip event will happen. And matching will subscribe to that event, update its status in database, and then pricing will also be subscribing to that end trip event. What will the pricing service do? Pricing service will be creating the invoicing and sending notifications, sending emails, invoice to the client, to the driver, whatever the business logic it wants to do. So that's how it will be. We are using direct remote procedure calls if microservices need to connect with each other directly, or if there is an async communication, we will be doing using Apache Kafka here. There are some trade-offs which we also need to focus. This trade-off was it's not a technical trade-off. It is mostly related to business, and it also impacts our technical functionality as well. The first thing is that should we inform all the drivers at once or one by one? And the main feasible approach is obviously, which also the Uber follows, is by one approach. So in case of simultaneous notification to all of the drivers, there can be some technical issues which can happen that when multiple drivers accept the ride at the same time, then how will we properly differentiate and to which driver we should assign the ride. This is a little bit bottleneck of this approach. So we'll go one by one approach. That is a better feasible and scalable approach here. Okay, these were all of the public APIs. Now we will be Grip service. I covered here that what it will be doing. Grip service will be doing the real-time connectivity between rider. It will create one public URL, one AWS Lambda function will be triggered when status of the ride is started and WebSocket's connection here. So on the client application side, we can use any mobile application like it is implemented, developed in React Native or in the Flutter as well. And obviously, the main package here will be the Google Maps package, which we will be using in the React Native application.